Well, hello everybody. So this video, I have a lot of the same stuff that I'm going to cover in others. I'm going to mention here, and that's just the way I'm going to do it. That's what seems right to me, is to not say something just once, but say it several times in the context of different problems. Hopefully let the ideas sink in as you see different problems solved. But in this particular video, I want to focus on linear functions. Linear functions in the context of average rates of change, delta y over delta x, versus instantaneous rates of change, meaning the derivative, or dy over dx. But yes, linear functions will be involved. What's a linear function? Well, it's if you plot the points that satisfy the function x and y, for example, you get a line. That's why it's called linear. Y equals mx plus b. B is the y-intercept, m's the slope, m to 1 is the rise over the run ratio. Anyway, okay, so that's our scenario. Now, as in the other videos I've given, I try to give situations that are not very complicated. Like, you could imagine doing this. It's not like if you learn physics and some of the stuff with electricity and magnetism is a little bit hard to imagine. Here, like, hopefully I'm giving you stuff that you can imagine no matter what, okay? So here's my scenario that I want you to think about. And if I get you to think about this, then we'll worry about how calculus is involved in it. So my scenario is this. Suppose there's a liquid that is poured into a container. Okay, so there's your container. Okay, how do the depth of the liquid and the volume of the liquid change together? So I would think like something like this is going to happen. For every extra centimeter of depth, you'll get an extra so many units of volume. Okay, something like that's got to happen. So for every centimeter, like say you pour it in there, it gets from what it is a centimeter deeper, then there's going to be so many cubic centimeters of extra volume. So change in the depth is going to cause change in the volume and vice versa. Okay. Liquids do take the shape of their container. So if this container is a cylinder, then we could say that the liquid that's inside of it is also a cylinder. And that would give its volume to be pi times the radius squared. And let's say for this particular problem, I'm going to say the radius is 7 centimeters for that container, times the depth or the height, whatever you want to call it. Since I'm talking about liquid, I'm going to call the distance from the base of the container to the top where the liquid is. I'll call that the depth, h. Okay. So yes, these two variables are going to change together. So calculus, and one thing that we use calculus for is it's the math that describes changes. When change in one variable causes change in another, calculus will probably enter the picture somewhere. Okay, and in this problem it will, and I'll show you how. So two questions I ask you to do. Okay, calculate the instantaneous rate of change and the average rate of change. Specifically, calculate the derivative of the depth with respect to volume when the volume is 12 cubic centimeters, and calculate delta H over delta V if the volume is 12 cubic centimeters and changes by half of a cubic centimeter. Okay, you'll get the same results. So I could just state as a brute fact that if the function that you start with is a linear function, and there's our function of the depth versus the volume. Okay, if that function that governs your situation, such as this one, is linear, then, okay, the average rate of change will be equal to the instantaneous rate of change. So that's going to be one of the themes of the video. And sure enough, if you do this, you'll get 0.0065. And if you calculate that, you'll get the exact same thing, exactly the same thing, 0.0065. Okay. All right. Now, where did that function come from? I didn't show you where I got that, at least not yet. I do want to tell you, though, it's linear before I show you where I got it. Why is it linear? Well, it's like this. H is the coefficient 1 over 49 pi plus 0. Oh, sorry. V times v plus 0. So it's like y equals mx plus b with different variables. M, the slope, turns out to be a somewhat a complicated number, 1 over 49 pi, but it's still a number. And then v, that other variable, is to the first power. That doesn't say v squared, okay? So this, let me get you to agree before I show you where I got that it's linear, okay? It's y equals mx plus b with different variables for our situation, okay? All right, now let me show you where I got that from, okay? And let me show you how I calculate both of these. All right, so we did say that when I started the problem, when I described the situation, that we would be pouring water into a container that had a radius of 7 centimeters. And the volume of a cylinder is pi r squared h. The radius is 7, so 7 squared is 49. Okay, so if we need a function that relates the depth of the liquid to the volume of the liquid, it's going to be v equals 49 times pi times h. Now, why did I present it to you this way? Well, to find the derivative, dh over dv, I need h, this variable on top, to be a function of v, this one on the bottom. So to find that particular derivative, you need h to be a function of v. So, maybe that's how you find the volume if you know the depth, but I need it the other way. I need h to be a function of v, meaning if I plug the v in and I do the math that's in the function, I'll get h, okay? So I'll get this. And then to find dh dv, we look at this formula and we use whichever rules are appropriate and we find the derivative of it. So what rule would you use if you had h is v over 49 pi? Well, I hope that you wouldn't use the quotient rule. I think a lot of people actually would, though. But let me again say that I'll deconstruct this. This is h equals the number 1 over 49 pi times the variable v. It's like saying, let's say, we'll give an analogy, okay? Suppose you had y is equal to 4x. What's y prime? And we've been over this before. We've learned the rules already. Well, 4x to the first power, y prime is 4. Okay, so this is 1 over 49 pi times v to the first power. V is the variable. So the derivative is going to be that coefficient, 1 over 49 pi. Okay, and notice here that there's no, if you say what's the derivative when v is equal to 12, there's nowhere to put 12. Okay, that derivative is actually a constant. So it's not like I plug 12 in somewhere because there isn't anywhere to plug it in. Okay, so it will be 1 over 49 pi, which if you calculate is 0.0065. And remember there were units. Okay, I said in the previous video I made that when we're talking about measurements like the depth of a liquid or the volume of a liquid in a container, then there will be units. You measure the depth, say, in centimeters, if those are the units that we're using. We measure the volume in cubic centimeters. So the units of this derivative are going to be centimeters per cubic centimeter. Okay, now that's a little bit of a strange unit to think about. I'm reasonably sure, I can't speak for everyone everywhere, that if you came across this in science class, they might reduce the units to centimeters to the -2 power, but that's not what I want to show you. I'll let the science teachers worry about that. What does that tell us? Okay, how can you interpret this number? If the goal is to do calculus and understand the number, what's that number 0.0065 mean? Well, remember when I started this, I said, I'm curious how the depth of the fluid getting deeper affects the volume of the fluid getting bigger and vice versa. If one gets bigger, so does the other. How does it happen? Okay, well, this will tell us how it happens. It says for every extra cubic centimeter of volume, we'll get about 0.0065 centimeters of extra depth. So if you were, say you were in chemistry class and you were in the lab and you were watching if the liquid could be poured in there at a constant rate and you're watching it get deeper and deeper and deeper, then for that particular cylinder with these dimensions to it, every time the depth, so H is the depth on top, every time the depth goes up by 0.0065 centimeters, if you could notice that, you're getting an extra cubic centimeter volume in there, okay? So that's what I wanted to figure out. How are the depth and the volume changing together? It's all in that number. You have to unpack it a little bit. You've got to know that the units on top are the depth units, which are centimeters. The units on the bottom are the volume units, which are cubic centimeters. You got to know that. But if you can unpack it all, that's the significance of that number, okay? All right. So that's what our derivative tells us then. It tells me how it's, as the depth climbs up, how the volume is changing. Now, that's for this part. Well, how would we do that one? Well, it's same way, but with deltas, with changes. So I took our same formula. The depth is the volume over 49 pi. In the question specifically said if the volume's 12 and it changes by 0.5, okay? So I started it at 12 units, cubic centimeters for volume, and changed it by 0.5, so 12.5 cubic centimeters for volume. Put that in here, 12.5. What are the units for this number? Depth, centimeters, okay. Delta H is this number minus that one. Oh, so that top number is in centimeters. The change for the depth, centimeters on top. Volume, this minus that, 0.5 cubic centimeters. 12.5 cubic centimeters, take away 12, 0.5 cubic centimeters. Divide that out, you'll get this. You'll get that same number, okay? So we could understand our units on the derivative from the deltas, okay? Now, all right, so I did it. I got that one for you. We got the same exact answer through either of these because if the function you start with is a linear function, the average rate of change, that's the deltas, is going to be perfectly equal to the instantaneous rate of change. So you could calculate either one of them. You're going to get the same answer. All right. So I wanted to show you one more problem where we have a linear function. And I'm just thinking of, or as I did this, I'm just trying to think of situations that are normal enough that your average person could understand it, such as a liquid in a container, right? You get the idea. So here's another one that anybody in school is going to be familiar with. That say you're taking a class and there's different kinds of assignments like quizzes and tests, and that they have different weights, okay? Quiz average, you average your quizzes, you know how to do that. Suppose that's 36% overall weight and the test average is 64% overall weight. All right, so say that's how the class is going to work. Now, here's the situation I would like you to consider. So you've got 2 out of 3 quizzes taken, and you've got all 3 tests taken. Let's say there's no more assignments in the class, and after you take this last test, there's still one more quiz that you need to take to be done. Okay? So quiz 3, to be determined, not yet taken, is the last quiz. Now, if in this situation here, G is the final grade in the class, and Q is the grade on the last quiz. So you get that, right? Because you could average all this together according to what the syllabus says, and you'll get G, a final grade in the class. And at some point, you will take this last quiz, but it's not known yet, so we'll call it Q, the grade on the last quiz. Suppose I define it all that way. What's G over DQ? Plus, could you interpret that number? Okay, it's not too hard to just tell me what this is, but to interpret it might be a little harder. But if you've been following the other examples, then I think you can do it. But I'll tell you. Okay, so first of all, if I am going to calculate this derivative, do you remember what I've said in the other problems? What do I need? You know, the derivative just doesn't appear out of thin air or anything. The derivative isn't these numbers, or it's not those numbers either. So what do you need to have to start with to get this derivative? Well, what I've said in the other problems, it still holds true, and it's the way this is going to work all the time, is I need some kind of formula where that top variable is a function of the bottom one. So I need G, the final grade in the class, to be a function of Q, which is what? The grade on the last quiz. I need some kind of formula where I plug in Q and I get G. I plug in my last quiz grade Q, and it calculates my final grade in the class. Okay, so there, I just wanted to get your thinking going by telling you that, yes, we need a function. G is a function of Q. Plug Q in, calculate G. To calculate dq over dg. So here, this is what the syllabus says, right? It said it's the test average. So there's the average of those three tests. That's 64%. And it says the quiz average with, I don't know what the last quiz is. That's why I represented it by a variable, is 36%. And that would be the grade. So that's how you do it. That's how the grade's calculated. I'll do a little simplifying. I'll take 95 and 70 and I'll divide by 3 and I'll get this number. I'll take Q and I'll divide by 3 and I'll get that one. This turned out to be 90.6 bar. All right. And I'll say divide that out, multiply by 0.36 and move it over with this stuff. That's what happens here. And I get 0.36 times Q over 3. That's this part. All right. And then 0.36 over 3 is 0.12. And if you calculate all that, you'll get 77.826 bar. So there's our function. G is a function of Q. So when you at some point know your last quiz grade, put it in here. That's what you're going to get as a final grade in the class. If you don't even take the last quiz, you'll get a 77.8. Okay. Now, once you have this function, what's the derivative? The derivative is the derivative of that formula with the rules that are applicable. And this is, again, linear. Okay? This is a linear function. If you plotted your last quiz versus your overall grade, all the possibilities would lie in a straight line. That's what a linear function is. It's linear because the Q there, the variable Q, is to the first power. All right? So, all right, well, your derivative is the slope. It's 0.12. If that's Q to the first power, the derivative of 0.12 times Q is 0.12. So there's your derivative. All right, so I got it. So to go back to our original question right here, I'll say dg over dq is 0.12. And that would be my final answer on it. Okay? Find the function for the situation, then find its derivative. So, all right, I got that. Now, I want to tell you something that I started the video with. If you have a linear function, which we would in this case, the grade in the class is a linear function of the score on the very last quiz. Okay? If you have a linear function, then the derivative is equal to the average rates of change. Now, think if you know that, what you could do to interpret this number. Okay? So there's our linear function. Here's our derivative. If the derivative and the average rate of change is the same thing, then doesn't that mean that however you want to divide that up, you could talk about the changes that way? So in other words, if I say the derivative is 0.12, and I could write that number if I wanted to, just for the sake of illustration right now, as 1.2 over 10. Okay? Is 1.2 over 10, is that equal to 0.12? Yes, okay. But if the derivative is equal to the average rate of change, any average rate of change, then that means that delta Q is 10, means that delta G will be 1.2. If delta Q is 10, delta G will be 1.2. Well, what's that mean? It means, well, every increase of 10 points on the quiz, delta Q, will cause an increase in the final grade by 1.2 points, delta G. Okay? Or any other way you want to do this. All right? So you could say like 112 over 100 if you want, but that's not as useful. Doesn't seem to be as important or applicable to say that if increase quiz score by 100 points, you'll increase your grade in the class by 112 points. All right. So yeah, we won't do that one. It's just not as instructive, but the number's equal to this, so we could use that. All right. So you could interpret derivatives that way in the case of a linear function. All right. The same thing is true with, I sometimes hear people say something similar with interest rates on loans, that for every percentage point the interest rate goes up, your monthly payment goes up by a fixed number of dollars or something like that. So that's also true because it's linear. But, one last thing. When I say this, I'm not saying any particular quiz grade gives you any particular overall grade in the class. I'm saying every increase of 10 points on the quiz will cause an increase in the final grade by 1.2 points. Getting a higher quiz score means getting a higher overall grade in this ratio or any ratio that's equal to that.